Good afternoon and welcome everybody to this session, which is on civil engineering and wind engineering. During this session, we have three speakers. Just a recommendation for the speakers: you have 15 minutes for your presentation plus 5 minutes for questions. And for the audience, if you have questions, please write your question on the chat. And the question will be answered at the end of the presentation. Okay, so we invite the first speaker, who is Marko Horvat. He's going to present CFD-based optimization of a wind-blown sand barrier. Yes, please come here. You have to speak close to the...
Okay.
Yeah, because the microphone is here, so you have to speak close to the...
Okay, I can even sit down.
Yes.
Okay, good afternoon, everybody. My name is Marko Horvat. I'm joining you from Wiki Limited in London, but during this study, I was actually affiliated with Politecnico di Torino. Yes, these are my colleagues, also Luca Bruno, affiliated with Politecnico di Torino, as well as Lorenzo Raffaele, and Sammy Chris, affiliated with OptiFlow, which is a consultancy company specializing in CFD. I will be talking about the CFD-based optimization of a wind-blown sand barrier. So I know this is a mouthful, so I will try to introduce you to the project where this study was done. What is the wind-blown sand, and what is the sand barrier? I will also try to just give you a brief overview so that you can understand what is going on in the presentation. Seems to be a bit slow.
Stuck you?
Yes. But yeah. I don't know. Maybe it's just slow. Oh, I don't know. Just skip the slide. Okay, just to give you a bit of a framework, this study was actually done during my PhD. And it was done within European Union's Horizon 2020 Research and Innovation Program. The project name was SMART, which stands for Sand Mitigation Around Railway Tracks. And it was mainly organized among three different organizations. The first being the University of Oxford. They specialize in aeolian geomorphology, and they were giving us all the nice information about the sand properties, the wind measurement data, and similar. The company that I mentioned, OptiFlow, they are a computational fluid dynamics consultancy company. They're based in Marseille, in the south of France. And Politecnico di Torino, which I was affiliated with, they specialize in wind engineering and applied mathematics. So it was the collaboration of these three organizations which led to results at this project. We also had a couple of industrial partners which are quite renowned in the railway industry, such as Reko Salchev Group, Astaldi, and Hitachi Rail STS. The motivation behind the study is quite simple. There's deserts. In the deserts, there's a lot of railways, and there's a lot of sand as well. And sand is quite adversely affecting the railway transport, and not only from the perspective of the comfort, but also from the perspective of the safety, excessive wear of the railway components, and so on. But the problem is not limited only to the railways, because other infrastructure is experiencing similar issues, such as roads, but also at the bigger scale, single buildings, but also the whole cities which are threatened by this massive dune you can see at the bottom of the slide. When it comes to the industrial motivation, as I said, 40,000 kilometers of railway is planned to be built up to 2030 in the MENA region. And from the scientific motivation, or better, the combination of these both of these aspects of motivation, there is no systematic approach in how people tackle this issue. So mostly they are just using trial and error approach and see what happens. So we try to make a bit of a difference in this perspective as well. So the first thing what we did is following civil engineering practices, we defined these two: serviceability and ultimate limit states. And basically we defined, okay, there are some serviceability limit states. These limit states are not so serious, but they are the ones which are reducing the efficacy of the railway transport and are reducing the comfort of the passengers. The most common one is the ballast contamination. And basically what you get is when sand fills in the void between the gravel that are on the railway tracks, you get much steeper railway track, which in turn gives you two issues. The first, the traveling becomes much more uncomfortable, and the second, the components such as wheels and rails themselves get worn much quicker. On the other side, the ultimate limit states, these are the ones which are stopping your railway traffic and are endangering passengers. So you can see here a couple of examples. Pretty much the most severe one is the trail derailment, when everything goes wrong and the train actually comes off the tracks. And yes, the problem with this and why trail derailment happens is because the sand is very incompressible. So when you have it over the tracks and the train tries to pass it, yeah, you can imagine what happens. In the same way, we started tackling this issue of the classification of the sand mitigation measures. And sand mitigation measures are basically measures which are installed somewhere around the railway infrastructure to stop sand from coming to the railway. Or if there is a sand, they should serve a purpose of removing the sand. So if you think about this section in relation to the railway infrastructure, you can split your sand domain into three different parts. The one is the sand source from which the sand is being eroded. So if you plan to build mitigation measures such as source mitigation measure, what you plan to do is you want to stabilize that sand bed. You want to stop it from eroding. The second part is this path. And this is the path sand has to cross from the source from which it is being eroded to reach the railway infrastructure, in our case, receiver. And in similar analogy, the mitigation measures which are put at this path are called path sand mitigation measures, which have main goal of these measures is to stop the sand which is already being transported. And then there is the third one, which is receiver. So these mitigation measures are positioned very close to the railway infrastructure, and what you want to do is either allow sand to cross the railway without being interrupted in sediment, or if there is existing sand, you want to use some aerodynamic properties of different, such as Venturi effect, to increase your wind speed, increase your shear stresses at the ground, and promote the erosion of this sand which is already there. When it comes to the physics of the problem, it is quite straightforward, not simple, but straightforward, because it's basically a two-phase problem. You have from one side wind flow and from the other side sand, and the wind flow is exerting shear stresses at the ground. And there is this well-accepted condition in Aeolian geomorphology, which says if you reach the threshold of the shear stresses exerted by the wind at the sand bend, you will have erosion. And this is pretty much what we used here in the study, and because it's an optimization study, so we needed something that is more simple. So we, at the beginning, discarded the multi-phase aspect. We said, okay, we have this condition, we will use this condition, and we will take a look what happens at the ground, and what is where the erosion and sedimentation is expected. Yes, we modeled our wind boundary layer with the logarithmic law, and yes, that is pretty much it in brief. When it comes to the optimization part, the procedure is again like people when they are optimizing always do. You have first some initial state, and you need some sort of automatic procedure, because you don't want to do all of these steps in a loop manually. So the first thing to do is to have automatic geometry and mesh generation, which is then here I was just using a simple block mesh because I will show you the geometry later. It's quite simple. CFD solver, which is in this case simple foam, because the only thing that we were really interested in was the shear stresses at the ground. Then I used a couple of Python scripts to assess my goal function, which in this case we wanted to minimize to get the optimal solution. And then optimization algorithms. So we used the quota, which is developed by Sandia National Laboratories. And yes, it's free to use and quite simple to set up. So yeah, we went with this solution back then. I don't know if I would repeat it if I repeated this study now, if I would use the same tools, probably not, but okay, to be discussed later. And first, I would like to start with this initial solution, because the geometry already existed and it was patented by Politecnico di Torino, because they've worked previously on this issue. And basically, what we are looking at here is the PET scent mitigation measure, which is basically a deflected wall, and it's a barrier which should generate as big as possible vortex, the upwind vortex, because what vortex is basically doing for you is it reverses the flow of wind at the ground. So you will either have sedimentation at that point because the velocity magnitude is lower, so the shear stresses are going to be lower, or you will have erosion, but in the opposite side. So it works well, no matter what the magnitude of the velocity is going to be. Further, what my goal was here is to take this initial velocity, parameterize it in a way, and then run the optimization loop on it. So my optimization variables here are the height of this vertical wall, the length of this curved deflector. I was called it deflector, but it's just a circle segment, and I had two of them. So it's basically these three parts which are of interest in my optimization part here. And how I define these variables came from the manufacturing constraints, because we had a manufacturer behind this who said, okay, you can build it in this way if you use our services and our materials. So the height was quite flexible. It was a continuous variable, but when it came to this these arcs, they said, okay, we have a couple of different variations of that. So we treated those as discrete variables in our optimization part. When it comes to the simulation loop, once again, we wanted to keep things simple, so we used 2D runs simulations for this. The calculation of the goal function, which is defined as a ratio of cost and performance, because there are basically two objectives. One is to reduce the cost. The second one is to increase the performance. And if you can do both, you are pretty much set. And then we used the gradient-based algorithms and also genetic algorithm as our optimization tools, just to see what happens and what can we get from both of them. And of course, this loop finishes when new geometry is or whether iteration finishes when new geometry and new mesh is constructed, because then you enter the new iteration loop. Yes. When it comes to the results, first, what I did, because my simulations were quite cheap, I did a big sanity check for myself, because it was the first time of getting introduced with the optimization part, and I didn't know what really can I expect from it. So I took like just a equally spaced variables, so the height of the vertical wall and then the length of the deflectors. And I ran a bunch of simulations. So, and what you can see here is that the cheapest solution. Okay, this is the plane where I plot the cost in relation to the initial solution, and also the performance in relation to initial solution. And basically, you find the point at 1.1 is the baseline solution performance and cost. And with this type of parameterization, you basically can see that all of the solutions, except for small parts over here, perform better. So this was encouraging. And basically, we've seen that the best we can do is to get the goal function defined like that of 0.79, and there was no way of going about it. I don't really know why, but everything was like that. And then you had a bunch of different configurations of the geometry, which gave you pretty much the same ratio of cost and performance. But again, these all look different. For example, if you take a look at the sample 4, 5, and 6, they're all showing you pretty similar result, pretty similar goal function, but they are quite different when it comes to the geometry, performance, and cost. And for example, if you take a look at the sample 1, this is the cheapest, but it's the worst performing one. And if you take a look at, for example, sample 3, this is the best performing one, but doesn't have the best goal function because it's expensive to build. This is pretty much how the field looks like. So you basically are expecting upwind vortex, and then the more you deflect your barrier, the vortex grows, and not only in the vertical direction but also in the horizontal direction as well. And this is then from these points and the shape of the barrier you can compute the size of your vortex. And then we started to then we tried the optimization procedure and see what can be done, how fast is it, and basically how do you compare it to this big sensitivity study we did before. And gradient-based algorithms are quite particular here because depending on the initial step that you start from, for example, this red and blue stars in this plot over here, you end up with a different final solution, because you will get only one solution, because it's basically a gradient descent procedure. You start from a solution, you go down the grade in the direction of the gradient of the goal function. And once you reach this 0.79, you will stop. And this is what happened twice here. So we got these two different barriers, which are quite similar when you plot them on top of each other, but are still exhibiting the same goal function. But of course, different cost, different performance. Probably because everything was so cheap and it was easy to run these simulations, genetic algorithm was maybe at least in my opinion, it's a better approach here, because you can then start with a population of a given size, and as you proceed and iterate over the iteration of the genetic algorithm, you get a cluster of points which is more and more pushed towards this limit that we've seen of 0.79, and then in the end you have a solution of multiple different barriers which are experiencing the same goal function. And then in the end, it's just a matter of client choosing which one works the best for them, because if they have a budget limit, they can choose the best solution given their budget. Or if they have a limit of a particular performance, they can do it the other way around. Yes, and this is pretty much it. For more details and when it comes to the setup and more results, there is a publication which is open access, so everybody can see it, and it's this one right here. Thank you very much.
Are there any questions from the audience?
I did, but I got discouraged quite fast because I said it was my first, introduction to the optimization. So yeah, it was a bit. I had a bunch of ideas of how do I want to tackle this issue, but I wanted to keep my life simple in the same way as well. Yes.
I have a question.
Sure.
So in your application, was there a real line application?
I actually don't know, because I was not in the contact with the group. I know that the other part of the PhD, there was some communication with the industrial partners. I'm not sure about this one, but I can check, and probably I should check, have a nice chat with Professor Bruno and see what is going on in this area.
Thank you.
Welcome.
Okay, thank you again.
Yeah.
I think we can go on. Okay, the next speaker is Louis Fliessbach. Please. Okay. Who is going to talk about dynamic stall of airfoils.
Yeah, okay. Thank you for having me. My name is Louis Fliessbach. I'm from Upstream CFD, and I'm talking today about an assessment of high-fidelity simulations for dynamic stall on wind turbine profiles. But before I start, let me say some words about us. So we are a small company based in Berlin And our expertise lies in high-fidelity CFD simulation, aerodynamics, and aeroacoustics. And our goal is to enable the industry to use high-fidelity simulations in their industrial design process. And for that, we are also part in different research projects. One of them is the Indiana Wind Project, funded by the German government and coordinated by Enercon, which is a big wind energy manufacturer in Germany. And one of our tasks was to build and assess an OpenFOAM process for high-fidelity simulations of dynamic stall phenomena on wind turbine profiles with sharp trailing edges in free-stream conditions. And therefore, all this work here is conducted in the realm of this project. And to start, some words to dynamic stall in general. So dynamic stall is a combination of complex flow phenomena caused by a rapid change of angle of attack. And this was first observed on helicopter rotors, but can happen basically on every turbo machinery. And therefore also on wind turbines. And the main sources of dynamic stall on wind turbines are blade oscillations, turbulent inflow, and periodically changing flow due to the rotation of the blade. And the main effect of dynamic stall is that aerodynamic loads can be much higher than in static conditions. And this is therefore really important for the manufacturers to know and to predict, because the blades become more and more structurally optimized. And therefore we need to study these phenomena, and this is commonly done by imposing harmonic oscillations of angle of attack on 2D airfoils. And this results then in this typical sequence of deep dynamic stall phenomena that you can see here on the right, where the profile goes through 6 different phases. First, the flow is mainly attached, and the increase of the lift is linear. Then we have a trailing edge separation that is forming and moving towards the leading edge. And during this phase, we have also the lift overshoot comparing to the static conditions. And then when the trailing edge separation reaches the leading edge, the flow gets massively separated, starting with a strong coherent vortex structure, which is known as dynamic stall vortex. And this vortex is then convected over the profile. And due to the pressure, the pressure peak of this vortex, you get really strong peaks in the aerodynamic forces. And during this phase of massive separated flow, after the dynamic stall vortex is convected, in some cases there are also secondary coherent vortex structures forming. And in the last phase, the flow is slowly reattaching before the cycles begin from start. So in order to simulate this kind of phenomena, we built an automated process for periodically pitching airfoils with sharp trailing edges. And this process was built for incompressible high-fidelity simulations by using hybrid runs LAS methods. But this can also be used, or was also be used to conduct unsteady run simulations. The whole process is based on a customized version of OpenFOAM V2012, plus some in-house tools, mainly our IO library UpCCO or UpSuite, which is basically a solver-independent library for efficient output, to efficiently output transient data. And in this case, this was particularly important because we wanted to be able to to output not only the transient data but also fast average data and flow fields. And this wouldn't be possible with standard OpenFOAM function object. So in total, we used different tools that you can see, here on the bottom. And the highlighted in blue are the tools that are either in-house tools or custom OpenFOAM versions. And the gray one are just standard OpenFOAM tools. One big part of the process was the meshing strategy. And the first question that we have to answer is how we realize the movement of the airfoil. And here we went just with the simplest method and rotated the whole mesh. Just also in order to avoid any overhead due to interpolation. The mesh itself was generated with snappy hex mesh. And we used two little tricks to reduce the cell count on the far field, in the far field, and try to mesh the far field with anisotropic cells, and only the blue area here with isotropic cells. Also, we only meshed half of the domain width in a span-wise direction in order to avoid, again, AMI interpolation. We mirrored then this domain, so we have perfectly matching cell faces at the cyclic boundary conditions. For the volume refinement, we followed basically the Spallard's guide to DAS grids and based the refinement zones on preliminary run simulations. And the result of the refinement zones can be seen here again on the right side. And concerning the prism layers, we were able to extract 39 layers, which for snappy hex mesh was pretty impressive. And this was only possible by using an O topology, and therefore we had to blunt the trailing edge a little bit. And the overall cell count of the productive grids was at 7.7 million cells for a span-wise extent of 1 port length. So for the double, if we increase the span-wise extent, it increase also the second cell count. Coming now to our DAS methodology. For the turbulence modeling, we used our Sigma DDS model, which is in gray area enhanced DDS version, published by my colleague and supervisor Marian Fuchs. And this one is also now available in the official OpenFOAM version since version v22.12. In addition to that, we used an enhanced DDS shielding function by Deck and Renard, recently published also. And with this shielding function, we ensure that the boundary layer is kept in runs mode in order to prevent model stress depletion and grid-induced separation. And here on the lower left images, you can see also how important this is in this case. The left image here shows the flow field with standard shielding function. And the black line is actually an isoline of the shielding function and shows a bit where the interface between runs and LES zones lies. And you can see that the shielding of the standard shielding breaks down completely and that the separation point lies much further to the leading edge than in the case of the enhanced shielding.
Just to let you know, we can't see your pointer. So if you
sorry.
point at the screen.
Thanks. Maybe can I, because also for the audience here,
Just use your hands.
get pointer options. Can you see it now? Yeah. Okay. So I was referring here to these two pictures. And concerning our the numerics, we used an custom pimple dim solver, which consists of consistent pressure velocity coupling with a low dissipation Riccio interpolation, and we also used a modified hybrid convection scheme. Coming now to our test case to test this process chain. And for that, we chose the S801 profile, which is an open geometry from the National Renewable Energy Laboratory with a sharp trailing edge. And for this profile, there is a comprehensive data set of experimental wind tunnel measurements. But here it's important to say that this data was only, we couldn't expect that this data fits completely to our free stream conditions of CFD because the test section was relatively small. And recent studies from Fliessbach and Garman also shows the strong influence of wind tunnel walls on dynamic stall phenomena. And therefore, we only expected a good agreement during the upstroke where the flow is mainly attached and not when the flow is completely separated. Regarding our flow conditions that we choose, we had a Reynolds number of around 700,000, a reduced frequency of around 0.1, and an mean angle of attack of 14 degrees, as well as an angle of attack amplitude of 10 degrees. And this should ensure deep dynamic stall phenomena. Okay. Overall, we conducted 4 productive simulations where we varied the span-wise extent and also the turbulence model, so the background turbulence model of the DDS, and as shown before, also the shielding function of the DDS. Coming now to the results, I will start showing you a short animation just to give you an impression of how the flow actually looks. And the first thing that we can see is that the simulation looks healthy and is well resolved. And the other thing is that we were able to capture all the main features of dynamic stall, starting with the fully attached flow, then the trailing edge separation going towards the leading edge, and then mainly also the strong dynamic stall vortex generated by the leading edge. But a little bit trickier to spot is then the secondary vortexes from the trailing edge, and the third one also from the shear layer that we will see in the forces. Now, here. And here I will just show you some comparisons. First, the comparison again between the different shielding functions, because here we had the biggest differences and improvements. So the standard shielding function was actually breaking down, and as we have seen, the separation point lied too much in front, and therefore we have here in green relatively strong underestimation of the lift. And we can see that with the enhanced shielding function, we are much closer to the experimental data and have rather good agreement during this phase of the cycle. Just some words to, because we did also a preliminary URANS study, and here we noticed that URANS is really sensitive to different setup decisions and was quite unreliable and depending on these decisions. For example, if we just slightly adjust the width of the trailing edge, gave completely different results. And this is also kind of the reason why we need to do high fidelity simulations on those kind of problems. And also we weren't able to get a real grid and time step convergence. So my last slide here shows you then the comparison with the experiment. And for this, I changed the plots to lift and moment coefficient, not over the angle of attack, but over the phase, because besides the good agreement during the linear upstroke phase, we have also really strong differences to the experiment. First one being that the dynamic stall vortex onset is delayed, and therefore all the next phenomena are fast shifted, and this can be seen in this plot really well. The other big difference is the strength of the dynamic stall vortex. All simulations predicted a much stronger dynamic stall vortex, and also the additional trailing edge vortex that doesn't occur in the experiment, and also the flow reattaches more rapidly during in the simulations. So, as I said before, we expected some differences, and we are pretty sure that the strength of the dynamic stall vortex as well as the additional trailing edge vortex are caused by the missing wind tunnel effects. Yeah, and this is based again on the study from Fliessbach and Garman. Yeah, here are just the main outcomes again, but I don't know what the time says.
Yeah, if you go for.
Okay. Yeah, so main outcome is we have a functional OpenFOAM process. Then the sigma DDS model is able to capture all the main features of dynamic stall, but also we have quite strong differences to the experiment during the path of complete separation. Where we need to do further investigation is why the dynamic stall vortex is actually delayed. This may be caused by the by a little bit too conservative shielding function from DEC and Renard. But yeah, here we need to do some further investigation. And yeah, thank you very much for listening, and yeah, feel free to ask any questions.
Are there any questions here? Yes, please.
Just a quick question. Are you, in your objective, is just a basic understanding what happens, or are you using this procedure to optimize the airfoil to performance, to do something there?
Yes, but as I said at the beginning, all this work was part of the research project Indiana Wind, which was coordinated by ENACON. So the industry is interested here in really understanding this phenomena. And as I understood, they mainly use simulations, not directly in their design process, but to feed their models in lower order tools. And these lower order tools are not so accurate, and yeah.
There is a question here. Can you read it so everybody can?
Yeah, so there's a question in the chat that's asked the presenter's mate, I think. No, the presenter's mode is being shared in the PowerPoint. I could
Okay, so.
Okay. Yeah,
No.
so this was later.
Too late. Maybe there is a very quick.
You were mentioning the airfoil. How many different surface levels did you use on the airfoil?
How many
Different surface levels in static extension.
surface levels?
Yes, surface refinement levels.
I had just one surface, so one level of the same.
So the level was the same.
Yeah, was.
Yeah.
Okay, there is another question, but I think you can talk later because now we are running out of time.
Okay.
So we thank you again. Now we move to the last presentation for today for this session. Josip Žužul is going to present about thunderstorm winds simulation.
Hello, everyone. Thank you very much for your attention. My name is Josip Žužul. I'm a postdoctoral researcher at the University of Genoa. And today I'm going to present you a shorter version of my yesterday's training session. So if you were there yesterday, I apologize. I'm going to repeat myself a bit. And the topic is going to be simulating thunderstorm winds in complex environments using OpenFOAM. So the outline of this presentation is going to be as follows. So first, I'm going to introduce you to downburst winds. Then I'm going to go straight to the case study, which is the thunderstorm case which hit Genoa. And I'm going to go step by step in geometry generation, mesh generation, setting up the case. I'm going to show you some results, and then finally I'm going to try to draw some conclusions and show you the future work perspectives. So downburst is a thunderstorm outflow, which is actually characterized by the vertical downward movement of cold air from the cloud base, which causes the divergent outflow in radial direction, forming the primary vortex ring. These winds are highly non-stationary, and they cause substantial wind velocities in the near surface region. The problem is that structures are generally designed on the basis of atmospheric boundary layer winds, characterized by the blue line, while the thunderstorms can produce the winds which have stronger velocity in the near surface region, which essentially result in the underestimation of design wind loading, which commonly causes the damage or collapse of lower structures. The case study I'm going to analyze today is the downburst in Genoa, and the event took place in August 2018. And for the present case, thunderstorm properties were detected through the installed monitoring networks, so through LiDAR profilers, scanners, radar data. So in particular, we had the downdraft diameter of the column of air of 4 kilometers, the touchdown location, the jet velocity going down, the storm direction, and the storm translation speed. The ABL properties were known based on the airport's meteorological data and radio sounding. So the relevant information about the case reconstruction is as follows. So we have two wind types. We have atmospheric boundary layer winds, which blow in the direction of 65 degrees with respect to the north. We have the reference velocity of 5 meters per second at the reference height of 3,000 meters. And the assumption is, as we have low ABL velocities, we assume we have neutral ABL, even though atmospheric conditions were unstable in the present case because we have a thunderstorm. And about the downburst, we have the storm direction of 30 degrees with respect to the north, and the storm translates in the velocity of 5 meters per second. So the case is gonna consider the larger complex area surrounding Genoa, which involves sea, hilly terrain, and buildings, which were considered for the CFD analysis of the moving storm, which is actually immersed in the background ABL winds. So we have ABL winds inflowing from the lateral sides, and we have the moving storm. And the idea of the case is to apply the dynamic meshes, which communicate through the partially overlapping sliding mesh interface. So the cyclic ACMI implemented in OpenFOAM 2212. The approach to create the geometry for complex environments is crucial. So we have to understand when we're building geometry for wind engineering analysis, because we can end up in a lot of troubles. So usually when you're modeling geometry, you don't have it actually. You have to model it on your own. And in the present case, it was exactly like that. So we had sea, hills, and buildings. And geometry was provided by the municipality of Genoa in DAM format and GeoJSON, which represent buildings. So for the terrain was generated based on the point cloud data in Blender, and that's fine. However, for the ABL inflow, we have to pay attention on extending the domain a bit and adding the artificial buffer region, which helps us to avoid having numerical instabilities. And actually, it makes it difficult to impose the inflow ABL profiles in our domain. It is important also to not apply any smoothing functions to change our terrain data, because we're gonna likely lose some buildings in the mountainous regions. So the buffer region was added at 2 kilometers on each side of the domain. And it is important, how do we treat this buffer region? So first 500 meters for the boundary is a 0 level height, and then we linearly increase it to the original dataset height. So this is the example of the terrain geometry. So 0, and then we linearly increase to the original dataset. So about the buildings, we move on to the buildings. These were presented in the GeoJSON file format, which is essentially a file in which we have the vertices of the building roof coordinates. So as in the Genoa, we have 200,000 buildings, which are organized in a very useful way. we adopted an automatic procedure for building generation. The procedure was as follows. First, from this data set, we extracted for every single data XYZ coordinates and 3-column files, and then we utilized the OpenSCAD, which is open source software, to automatically create the buildings in the following way. So this is the original data set. We extract X, Y, Z coordinates, only this part matters. We store them in the building one TXT file, for instance. We process this data in a way, so we round the Z coordinates to the nearest 0.5 meter. And we remove clusters of points, because we can have false data in the input. So if you have a cluster of points, we just collapse it to one single point, because otherwise we have problems with the STL rendering. We apply the OpenSCAD software, which is programmer's CAD software, and it allows us to generate the STL of a lot of buildings by programming. So we applied the Python library, Solid Python 2, which helps us to make this job easier, because OpenSCAD is not very user-friendly, let's put it that way. This is an example of the Create Buildings Python script, in which we actually loop through all buildings, and then we extract, so from the files we created, we create the polygons for the building shape, so consisted of X, Y coordinates, and we create a linear extrusion based on the height. And actually, from that, we export, we return all buildings, we collect all these buildings created in this way, the linear extrusion, and we compile the SCAD file, which is basically, we just render this file from the OpenSCAD, and we generate the entire all buildings in the area in quite simple way, actually. So if you walked around Genoa, you realize most likely that it's a very complex area. So you have a lot of gaps, a lot of buildings, and it's a mess to mesh this. So to make this case a bit easier, I'm gonna just isolate and focus on one single building, but the approach still remains the same. So first I'm gonna create the bottom mesh of the domain, and then I'm gonna initialize the ABL in this case. Consists of bottom mesh only. Then we're gonna create the sliding mesh, which is gonna slide on top of the bottom mesh, and we're gonna finally run the entire case. So we created the block mesh through the block mesh dictionary. We create the block mesh generated grid only close to the surface. So we have north, south, west, east, top, and bottom patch. Quite straightforward. We apply the surface feature extract to isolate all edges. So we use include angle 180, and we extract the emesh file. We then proceed with a snappy hex mesh, and we use our terrain, STL, and buildings files. And it's important to divide the STL before to different roughness classification areas. So if you have terrain and sea, which have different aerodynamic roughness lengths, we divided this earlier. I did it in Blender. It's quite straightforward. And then we apply the refinement close to the features, like feature edges, refinement close to the areas. And finally, it is also important to use, at least in my experience, to use a 0 for the resolve feature angle to properly create the mesh. Finally, we have the snap hex mesh generated grid around one single building, and this is for the bottom mesh case. In terms of creating the second mesh, which is the sliding mesh, it was built through the M4 macro, and the grid was constructed in the following way. So we have the storm inlet, so 4 kilometers diameter, 8 is in total for the entire disk. We have this, I call it storm outlet, side part of the inlet, which is like a safety to allow our storm to develop. We have the storm sides and the sliding patch. So we got the sliding patch is at the same height as the top of the bottom mesh. So this disk is gonna slide on top of the bottom mesh. So now we're gonna proceed with the ABL initialization, and in that perspective, we're gonna first use the create patch to merge the patches through which we want to initialize the ABL inlet. Because usually what you do is you're gonna investigate various ABL inlet directions, various angles of attack. So for various directions, you're gonna possibly change the patches which we want to group. So we collect the patches west and south for the ABL inlet, and the other ones for the outlet. Then we define our ABL condition properties, for which the relevant ones are the reference velocity, the reference height, and here it's important to distinguish between the Z0 of C and of the terrain, because we have different properties of these patches, which we're going to specify later on. Relevant information for the velocity are the boundary conditions in terms of the atmospheric boundary layer inlet velocity specified at the ABL inlet patch. Actually, we include all things we specified in the file earlier. For the top patch of the bottom mesh, so we are considering only the bottom mesh only at this point. It is important to specify the fixed shear stress because you're not going to maintain the ABL profile you initialized earlier. In terms of K, we specify the atmospheric boundary layer inlet K. Again, all information previously described in the ABL conditions file. This is standard for the omega specific dissipation. We apply again the corresponding boundary condition, atmospheric boundary layer inlet omega. The rest is pretty much standard. And for the turbulent viscosity, it is important to focus on these two different patches, the terrain and C. So we apply the atmospheric Newton K wall function, and we specify the different Z0, so aerodynamic roughness length, which is associated to this patch. So we invoke the terrain and Z0 for the C. This is standard. So this slide would show the ABL initialization field, which is conducted through the steady runs simulation. In terms of the moving storm, so we want to merge these two cases. First, what we do is we merge the meshes. So we take our case where we have the bottom mesh, and we merge with the sliding mesh. And then we have to, when we merge the grids, we have to introduce the interface through which two grids will communicate, because we want to impose the sliding, the movement of the top mesh. So for that purpose, we have to proceed with the topology set. So we have to first collect the faces, which would form the sliding mesh interface. This is the moving face. Moving phase zone set, which is basically derived from the sliding patch of the top mesh, and the fixed one. We use the toposet dictionary for that purpose. The second step is to convert the internal faces into the boundary faces, which requires the cyclic, which creates 4 different patches for the cyclic ACMI. So we create so-called couple blockage patch pairs, ACMI 1 and 2, a couple of blockage patches. The third step, when we created the interface between 2 regions, we want to collect all the cells which are assigned, which we want to assign the moving component, and for that purpose we use the topology set. And what we do is actually in the toposet dictionary we define the point which is located in a region, which is located in the top region. We use we create the new cell set, which we're going to call the moving cell set. Based on this moving cell set, we convert it to the zone, and we call it the moving zone. So to this entire zone, we want to apply the translational motion, which is defined in the dynamic mesh dictionary, by imposing the corresponding information in the velocity for the velocity input for the moving zone part. So these values are defined based on the storm velocity and the angle through which the storm is propagating. In terms of the velocity file U, in these new created patches, we have the UX and UY, which are defined based on the storm translation speed and storm direction, because these values correspond to the transfer of horizontal momentum between the moving storm, and we want to apply this also to our patches at the inlet of the moving storm, and the vertical velocity, which corresponds based on the full-scale measurements. To the blockage patches of the ACMI patch pairs, we impose a fixed shear stress. The rest is kind of standard. So finally, we merged the meshes. We created the cyclic ACMI interface, and we want to run the case. For that purpose, we're going to use the pimple foam, but we force it in the piezo mode. And we specify the libraries related to the atmospheric models and the finite volume motion solvers. And this is what we get. So we have the, in terms of the results, I'm going to quickly show because I'm running out of time. We have the velocity field at the horizontal plane at 100 meters. We have the storm, and you see that the velocity field created by the downburst is way stronger, more intense with respect to the ABL winds. And for 3 different time steps, I'm going to show you the slice along the storm direction for 20 minutes. 25, 30 minutes, we have this, the top mesh, which is moving along the top of the bottom mesh. We create the vertical cone falling down, the vortex, which is generated on both sides, and we have strong velocities at the front. Finally, just to show you the zoom around the building. This is our building, quite poor. The storm is falling vertically on it, and you see that the velocity field and the velocity vectors show that quite strong, intense velocity happens here. And of course, we have because the topography, we have the acceleration of the flow inside this valley. Finally, just quickly, I'm going to show you some comparison with the LiDAR data. I have to check this more in detail, but because the data based on the LiDAR data is not very, it's difficult to handle, let's put it that way. So sampling frequency is low, and sometimes it's a mess. But based on our current understanding and the different time steps which we compared with the LiDAR data and with our still a simple case where we have only one building, the trend seems to be, let's say, in line with one with the other. And finally, I want to sum up the presentation. So I show you that it's possible to automatize the geometry generation procedure in case we have a huge number of primitive objects. Block mesh and snappy hex mesh show to be a reliable tool in the mesh generation stage for complex mesoscale areas, and OpenFOAM can certainly be used for the thunderstorm downburst wind analysis in complex environments. And finally, for the future work, we're going to extend the analysis to involve a large amount of buildings. And we're going to perform the in-depth analysis of the result comparison with the available full-scale measurement data. Hereby, I would like to stop. I think I have more time. Thank you very much for your attention. And if you have questions, comments, please ask now or talk with me later on. Thank you.
So any question from the audience there?
Yes, that's right. Okay, I see. Thank you very much for your question. The thing is, when we're dealing with atmospheric phenomena, we are more often than not certain about a lot of things. So based on the radar data, we have seen the storm is generally moving with the average velocity of 5 meters per second, generally. Sometimes in some region, it's like 2 to 3, in the range of between 2 and 3 meters per second. Sometimes it's 6, but on the average should be 5. So we applied some simplifications because first we want to understand if we can run it in the simplest possible way, but not simpler than that. If we can understand, if we can get the comparison which is reasonable, then we might consider changing the velocity, like keep it in the rate 2 meters per second, then ramp it up to 5, then reduce it down to be more realistic, if it's going to be possible. But now we just use, okay, let's put it on the average it's 5. Let's run it that way. Thank you.
Other question here? Okay, there are a couple of questions. Can you please read them so everybody can share? And maybe there is another one there. No, this is the
This is
previous
all.
one.
Okay.
For forgetting. These two. Read.
Okay. Okay, so I'm gonna read the question. How is the 5 meters per second at 3,000 meters measured? Okay, so this data relates to the so-called radio sounding data. These are data which is like measurements which are performed by the atmospheric models meteorological actually community. They release the atmospheric balloons. They lift them up at 6, 12, 18, 24 UTC, and then they measure the properties along the vertical. So this is how we got 5 meters per second at 3,000 meters. It's not that we placed something there. Okay, I hope I answered your question. And then the second one by Theodore. Could you please repeat what you mentioned that according to your experience should be 0 in snappy file to create a proper mesh? Okay, you want to resolve the angles. That's the thing. If you want to resolve all, if the angle is not specified to 0, so if you put like 30, you're not gonna resolve all edges. So you want to resolve all edges. That's the point. You want to use this featured edges. You want to resolve your buildings there because you have sharp edges. You want to make sure that your mesh is properly built there. Any other questions in the audience online or in presence? This is the old one.
Yes. Okay, so thank you everybody for attending this session. We close the session now, and yeah, there is no other session. Thank you.